and seasonality before your prediction. And this thing should be done, okay, for the statistic model such as like ARIMA or weighted moving average models, but for RNN, okay, removing trend and seasonality sometimes also help a little bit, sometimes, but it's not always. And the help you get by removing trend and seasonality is not going to be a lot, okay, because RNN is a much powerful model, okay? It can not only learn the time series behavior, but also it can learn the trend, seasonality, okay, supposedly. Okay, just want you to be aware, okay, about this thing and why we need to do that. And in certain situation, we need to, in what certain situation we need to do that. Okay, so when using RNN, it's generally not necessary to do all this, but it may improve performance in some cases. Okay, since the model will not to learn the trend or the seasonality. Okay, so it's not necessary that you have to do this for RNN. Okay, so that's now, okay. Try to, as I say, like that simple RNN is not performing very well. So let's try to, create a much more complicated RNN and see if it performs better. Okay, so so we can stack multiple layers of cell. Okay, as shown in the figure in the next slide, something like this. Okay, so now, okay, we use 3 simple RNN layers. Okay, we could add other types of recurrent layers, but we haven't talked about the GRU yet. We will cover GRU later. So this one is again very simple. Model equal to Keras models. Sequential API. The first layer is simple RNN. We have 20 neuron, 20 recurrent neuron, and we have return sequences equal to true. Input shape is none. Okay, it accepts any length of the input, and it's going to output, 1. Okay, and then, so this is input shape. Okay, this is not output. I'm sorry. So anyway, the Keras layer simple RNN. The second layer has 20 recurrent neuron. We also said return sequence is equal to true, and the third layer is the output layer. We have 1 recurrent neuron, and that's it. Okay, and for this one, we will only output the less output. Okay, so keep in mind for the other for RNN, normally we would like to all the other layers to set. We would like to set recurrent sequence to be true for all the other layers, except the output layer. Okay, because the output layer we only want the less output. Okay, for this time series data. Okay, so and the reason to set return sequence to be true is because okay, without that, okay, then this thing is going to only output 1 number instead of 1 sequence. This layer is going to output only 1 number. Okay, but this is not what we want. We want this layer to output sequence, right? Same thing, we want this one to output the sequence. Okay, so that's why. Okay, sorry. So we have return sequence to be true for the first layer, second layer. Okay, and once we have that, okay, of course, we can unroll through time. We can do the unroll through time. So this model is going to be something like that. Okay, and then, okay, so except this, I think I already explained that. Okay, so so if you compile, fit, and evaluate this model, okay, you are going to get like a MSE of 0.003. Okay, this one is better than not only naive forecasting but also that perceptron model, right? So this one we finally beat the linear model. Okay, and think about how many neurons do we have? We have totally 41, right? So in terms of number of, we do have like more number of parameters in this model. Okay, we do have more number of parameters in this model, but we also outperform the linear model. Okay, so so the last layer, okay, we don't like the last layer, okay, in this model. Okay, the reason is we want to forecast a univariate time series, and so we must have a single output value per time step. But having a single unit means that the hidden state is just a single number. Okay, that's not much, but it's probably not that useful. Okay, because iron will mostly use the hidden state of the iron recurrent neuron, okay, recurrent layers to carry over all the information, okay, from time step to time step, okay. So it will not use the final layers hidden state very much. So that final layers hidden state is kind of like it's a waste, okay. And having that, what should I say, like the feedback mechanism in the last layer is also useless. Okay, so instead of using RNN, the recurrent neuron in the last layer, okay, we can replace this output layer with a dense layer. Okay, because once you replace that with a dense layer, you no longer need to process the feedback in the last layer. So it's going to run slightly faster. Accuracy will be roughly the same. Because as I mentioned earlier, okay, in the last layer, in the output layer, that hidden state is not going to be used anyway, right? It's not going to be used anyway. Okay, so we are doing something like this. Okay, so return sequence equal to true. But for this one, okay, chaos layer dot simple RNN, the second layer, okay, we don't set return sequence equal to true. Why? Because the last layer is a dense layer, right? Because it is a dense layer, it does not expect the sequence input. Okay, if this one expect the sequence input, like what the model that we have earlier, this one expect the sequence input, then the previous layer, okay, if it's also formed by recurrent neurons, then you have to set return sequences equal to true in order for this layer to output a sequence. But this one, because it's a dense layer, so it does not expect the previous layer to give it a sequence. So we don't need to set the previous layer's return sequence equal to true here. Okay, and we also only going to need like one neuron in the dense layer. That's it. Okay, so if you try to train this model, okay, this model actually converges faster, performs roughly the same. Why does it converge faster? It is because, in terms of complexity for the model, this one is easier. After all, the dense, the regular neuron is supposedly much easier than the recurrent neuron. Okay, so this model is easier. So since this model is a simpler, so it converge, the training converge faster. But it performs roughly the same as I already mentioned earlier, and also, we can even change the output activation function if we want. Okay, if we want this to confine the output to be within certain range, then you can incorporate certain activation function in this regular neuron. Okay, without any problem. Okay, but in the previous simple RNA, you cannot do that. Okay. So, so far we only predicted the value of the next timestamp. Okay, so how about if we want to, predict the value several time steps ahead? What do we do? Okay, with the previous 50 value, we predict next value, right? So sometimes we want to predict not only the next value, we want to predict like maybe next 10 values. So a naive approach is that, okay, we predict one value first, and then use the previous 49 value and this new predicted value to predict the next value, right? And we can do this repeatedly for 10 times. And then we can get the next 10 values, right? So this is, naive. This naive approach obviously it works for this type of question, but there are some issues for that, okay? This first option, to use the model we already trained, make it predict the next value, then add that value to the input. And so this is exactly what I just mentioned. Okay, so the code. Okay, here. Okay, series equal to generate time series 1 n steps plus 10. Why do we need to do the plus 10? Because now the ground truth is not 1. Is we want the next 10 values. Okay. So here, okay, we just 4 step ahead in range 10. So we want to do this 10 times. Okay, every time we just use the previous 50 to predict the next one, and then shift one step ahead, and then do the same thing repeatedly for 10 times. And but this, even though this works, but you will find that, okay, the accuracy of your prediction is going to go down more and more as this iteration, goes on and on. Okay, so here we have an example. Okay, the naive approach is terrible. Okay, if you use like a naive approach, it gives an MSE about 0.223, but the linear model gives an MSE about 0.0188. It's much better than using our RN to forecast the future one step at a time, and also much faster to train and run. Okay, let's just use this figure. That's easier to see. Okay, you can see the blue, the red point, the red dot, are the ground truth, and the blue cross are the value that we forecast. Okay, by using this iterative approach. So you can see that, okay, the next one, the ground truth and the predicted forecast is match very well, right? And the next one, and so on. So the next few values, well, it's a little bit off, but not much, right? But this thing becomes more and more, further and further apart from each other. You can see by the 10th value, the difference is like significant, right? Why? Because this error gets accumulated. The error will get accumulated if you use this way to do the prediction. Okay, if you use this iterative way to do the prediction 10 times, because the next prediction is built on the previous prediction. So which is not ideal, okay? So what do? Do we have a better way to resolve that? Okay, let's take 10 minutes break. When we come back, let's continue the discussion, okay?